Okay, maybe I can just start talking. So thank you very much for giving me opportunity to talk about this in this workshop. I'm so excited to join this. So my name is Taichi Kawamura from Institut de Physique de Paris, and I might be quite a stranger here because I'm completely not the gravitational wave or astrophysicist. I'm a geophysicist who's usually working on lunar seismic data and Martian seismic data. So I'm completely new here, and I'm very excited to find new things. And I'm so excited to see that so many people are now interested in lunar seismology. It's so exciting. So today, I will talk about the moon. And of course, oops, it's not moving. Why is it? Yep. And especially the seismic observation. So I just want to remind you what Apollo mission did. It was a mission from 96 to 72. There was a 6 landing. Especially 5 of them carried a seismometer. I will go into details. And I should remind you, it was not really a scientific mission, but science was just a piggyback. But still, it gave us lots of information on the moon, which is already still important today. And if I were going to talk about the moon, I have to start with this picture, because there was an attempt to detect gravitational wave on the moon by Apollo 17. So this was lunar surface gravimeter, which also Jan pointed out. So this was proposed by Weber, but you have a similar concept as we are discussing today. However, there was a malfunction of the instrument, and the detector could not provide any meaningful information in terms of gravitational wave detection. And we can also see that Jack Schmidt, which is the only geologist who went to the moon, placing this gravimeter on the moon. And I think maybe I should skip a little bit of this movie, because sometimes people think that sending astronauts solves everything, but it's not as simple as that, because I see that he's wiggling around, stringing around, and I also have another movie that he just falls on to the instrument. And so it's not simple to place instrument on the moon. But still, this was a very interesting opportunity, and we have many lessons learned from this. And though this LSG, lunar surface gravimeter, did not provide information on gravitational wave, it did function as seismometer. And actually, this was one of my first project when I entered the academic career, to use this LSG as a seismometer. And we discovered that it was functioning as a seismometer. So it was nothing. It brought us some interesting information to us. So with that said, let's move to seismic observation, or more in general, geophysical observation we made on the moon. So basically, this is an Apollo network, almost triangular shape network on the lunar near side, and we have heat flow probe, magnetometers, and laser reflectors. So this was really an almost complete geophysical station that we deployed on the moon. And here, of course, we have this seismometer. And I just want to point out that something I mentioned yesterday. So this skirt is to protect this from the thermal noise that will come into the seismometer. And this was not there during Apollo 11. And this was something that was added afterward. So Apollo passive seismic experiment, what was it? So here is a seismometer. So you see the difference between the two. So this is the thermal insulation they added afterward. So the observation period was 96 to 77. 5 stations was deployed. Unfortunately, Apollo 11 could not survive the night, so it's stopped the observation. So when we say Apollo seismic network, we mainly focus on 12, 14, 15, and 16. So all of my discussion will be based on the observation of these networks. Just to give you some idea what of the things that we have seen. So we saw many different kind of seismic events. So for example, we saw natural impacts. So it's a meteorite impact that hits around and shakes around. And you might also remember we saw something similar on Mars. This was also observed on the moon too. Artificial impact, this is we just dropped a part of the rocket that we don't need anymore to create the to have some active seismic experiment. And I would say this was a controlled experiment, so we know exactly where it hit. So it is still one of the key observation that we have to constrain the lunar crustal model. Then we also have shallow moonquakes. So these are the biggest moonquakes that we observed. And this includes the magnitude 5, the biggest one that we observed. But it's rare. During the 7 years observation, we only had 30 of them. So large portion of the seismic event that we saw was deep moonquakes, which occurs about 900 kilometers in depth, which means almost half the way down on the lunar structure. And there was almost 8,000 events observed during the mission. And what is interesting is that their detection is correlated with tidal period, which means that these deep moonquakes are tidally triggered events. So this is something interesting that we saw. So we have these kind of primary moonquakes, and I would like to invite you to the talk this afternoon. We will have a summary of ISRO from Professor Nakamura, who has been working on moon data since Apollo era and who's still active today. So, excuse me? I couldn't say. Actually, this is in minutes. Sorry, I should have, sorry, it was a very good question. I should have mentioned that. So it's in minutes. So, okay, if you have ever experienced the earthquake, which is not always the case for when I talk to Europeans, but it's basically the longest one is about a minute. From my experience, the longest one I experienced was Tohoku 1. It was about a minute, but here it can go up to hours, which means that when it's hit, it's continued to ring. This is because of the extremely dry condition of the moon. So the attenuation factor is so attenuation is so low. So once it's ring, it continues to ring. Yes, thank you very much. It's a very good point. Yes, and I also want to point out one event that is not necessarily a center of discussion when we talk about seismology, because this is called thermal moonquakes. This is a crack of the surface rock or surface itself due to temperature variation. So here is the detection, and you also have the arrow in sunset and sunrise. So what happened is due to the temperature variation at the sunrise and sunset, the rocks crack, and they can be observed as these kind of signals. So there are some studies that to use these as an ambient noise of the moon. And after I saw this distribution of permanent shadow region, maybe we might expect these kind of thermal moonquakes at the edge of the permanent shadow region. So let's talk about noise. So this is kind of like a core of my presentation today. I can talk about this for hours, but I will just try to walk you through this plot. So first of all, I would like to draw attention to this gray line, which is the noise level of the Earth. I took the data from Black Forest Observatory, which is one of the most quietest station in Europe, and this is the noise level. So this is what we call the microseismic peak, which is coming from an ocean. So in other words, wherever you go on the Earth, this peak will not disappear. In other words, this frequency band, we can suppress it, but it's always there. And this part is, in a way, we are in the blind if you keep observing on the Earth. And now I would like to draw attention to this color part, which is a noise variation of the Mars. So this is again the histogram frequency by frequency, and the yellow part is a peak of the histogram. So at low frequency, we have almost peak distribution around 10 to the power of 9. But during the day, you see a large variation of the noise, and this is due to atmosphere. On Mars, atmospheric activity is much more strong during the day, and on the night, it stops. So what happens is that during the night, we almost hit this black line, which is the theoretical prediction of our instrument noise level, and we almost hit that. On the other hand, if you go during the day, you see much higher noise, which is basically due to the atmospheric activity, which is shaking the ground, shaking the lander, and everything. So basically, these things are coming from atmosphere. And I can also point out that this microseismic peak, which was always existing on Earth, is not anymore visible on Mars. So with this, we proved that there's no ocean on Mars. So first of all, this was already something exciting for Earth seismologists because this part of the frequency band was something not visible, or not always easy to see. And once we go to Mars, it's clear as it's just going on following the theory. So it's something we can benefit from really by going out from the Earth. And I also want to show you this red curve. So this is a noise level when the seismometer was on top of the spacecraft. So before we deploy. So this is basically the benefit we had by placing a seismometer on the ground. And you see all of these noise peaks. And these are all coming from, basically we think that they come from the lander itself. So these are all the mode of lander. And since there is a wind shaking, by the way, so we have some limitation of the observation, and this is during the day. So when there was a strong wind. So there was a wind blowing on lander, which excites all the lander modes. And this is seen as a main source of the noise during this time of the day. And I would like to also point out that though we placed on the ground and we suppress the noise, the peaks are still there. So that is why I say that one of the most main source of the noise is coming from a lander. And I remind you that inside we placed about a meter away. So of course, this is constraints of robotic deployment, but this is something we always have to keep in mind. And finally, I will come to this white line, which is a noise I get from Apollo. So this is like a highest, noisiest part, and this is a quietest part. So first thing we can see is that at this frequency band, 1 to 10 Hz, we are almost competing with InSight, which is most quiet observation we ever made in with a seismometer. But at the low frequency, it increases. But this is not really the problem of the noise, but it's rather a problem of an instrument. We know that even what we call the long period seismometer of Apollo, we start to see the degradation of sensitivity over here. So we think that this is much more instrumental compared to environmental. And this is one of the arguments we see that we really don't know the true background noise of Apollo. But we still, okay, first of all, we don't see microseismic peak, which is good. And we also see that at high frequency, we are already seeing something very low. And I won't be surprised when we have a broadband seismometer, this can go down to this level. So this is something we can discover in the near future. So even by checking this background noise, we see that moon is very quiet in terms of seismic signal. And given that atmosphere is not there, we don't expect this atmospheric noise we see on Mars. So this is a very quiet place in terms of seismic noise. But we also have moonquakes. So what can they tell us about? What are they going to create in terms of noise? So here we are transitioning into this Apollo era to modern BBB. So what we look like this should be looking like this. This will be, so this is just a plot of distance and amplitude that we expect for various quakes. So this is what we saw on Apollo, but we are expecting to see much smaller amplitude, which is based, for example, reflection from the core. So in addition to seeing more signals, we will see more noises, of course. And these are the kind of like a summary of the spectra of impact and deep moonquakes that we observed during Apollo. So based on this, we would like to do some models to predict the noise condition of the moon. So how are we going to do this is we just simulate the seismic signal that we expect. So this is one example. I just took a big shallow moonquake and just made a displacement Z and E in spectra, acceleration, and put this in the spectra. And here you also see the comparison between the seismometer we have and the seismometer that we will have. So if it exceeds the red line, it means that it will be visible in our seismometer. By the way, this is from 10 to the power minus 3 Hz to 100, so it's 1,000 seconds to 100 seconds. So we are talking about very long period. So by using this, we can simulate the expected signal from single moonquake. But then we also have to take into account the size frequency distribution. And for this, we just take what we observed in Apollo. So this is a size frequency distribution. So on y-axis, we have a number of year, and this is you can see it as a magnitude. So we have, if you follow the red line, which is a meteorite impact, we can extrapolate what we observed during Apollo to predict how many smaller impacts we will have. By doing this, we can simulate what will be detected on the seismometer, which will give us this seismic noise on the seismic background noise that we can expect from impacts. So this is exactly what Jan showed in his presentation from Ronione et al. 29. So this is what we call seismic hum or background noise coming from impact. And we also like to say that this was not a bad model, because now we have some observation from lunar impact flashes on smaller size impact. So various observation also shows that this also follows a nice line. So this will end up in the displacement spectra of about 10 to the power minus 13 to 14, which is shown in previous figures. We can also play the same game for deep moonquakes. So this looks exactly the same figure, but actually it's not, because this on the bottom, this is based on actual Apollo observation. So again, I just extrapolated the size frequency distribution of deep moonquake. So this is what we observe from this distribution. And let's put this 7-year observation to a day observation of a day, or 14 days. So this will decrease the magnitude for sure. But the distribution itself, we say that it keeps the same distribution. So with this, we can also estimate the noise level from the deep moonquakes. So this is what we expect. So this is time in x-axis and y in frequency band. And the color is basically the noise level. So you see that if you see it in a vertical displacement, the noisiest part, it will be like 10 to the power minus 12. But basically at between 10 seconds to 100 seconds, we see typically 10 to the minus 13, minus 14 level of noise level. And if you see it in acceleration, the number will change, but basically the idea is always the same. Basically, you will have something even lower than what we observed on Mars. So even from this, we can also expect that even though we have deep moonquake, which is the most largest portion of the seismicity we observed on the moon, even we're taking into account these seismic activities, the seismic noise is pretty low compared to what we know or what we see on the Earth. Finally, I would like to have some word on the coherency of the seismic signal. So we did some theoretical studies to say that, let's say there is 2 seismometers placed on, it is 100 meters, sorry. So this is, we simulated the seismic signal in this box from 100 kilometer away impact. And to see if you have 2 stations side by side on 100 meters away, how the signal will be correlated. So if you see yellow part in this figure, so this is X to X, Y to Y, this is, yes, Z to Z, X to X, Y to Y. And you also have cross correlation, ZX, ZY, but basically it's a correlation of 3 different axes. So what you see is that if it's yellow, the noise is completely not correlated. So which means that, of course, the cross correlation is completely non-correlated, but even if you compare Z to Z, you quickly reach something yellow, which is almost no coherency between 2 events. And this is 100 meters side by side. So this is a good point of this, is that if you want to detect, if you want to say that noise is stochastic, you don't have to go far. You can just go 100 meters away and you see the noise completely different. But if you want to use this to correct for the noise, saying that two should be seeing the same noise, it might be a problem because noise is not correlated at all. But this is something we might discuss further. But this is simply some result we got from numerical studies. So this is just to summarize some scientific requirement. I won't go through everything. So we have various scientific goals and sensitivity that we need. And basically, I think that I would like to draw your attention here. So this is how better we should be compared to Apollo. So if you want to detect core reflection, we have to 10 times better, 50 times better. And if you start to go to like dwarf merging and black hole merging, you have to go at this incredibly high sensitivity, which starts to be challenging. But okay, for us, we are still in this regime where we want to detect seismic signal. So we are now developing a new seismometer called Lunar Optical BBB. We just call it LOVE-BB. So this concept is to remove the mechanical part of our Mars seismometer and replace it with the optical sensor. So with this, we can remove the complex part, and we can also remove the feedback part, which is also a source of noise. So by this, purple line is what we got from InSight, and we are going to, we are aiming to reach this frequency band, which is 10 to the power minus 11. So we are now trying to make this seismometer, and this should be ready very soon. So just to give you some better ideas, so this can be split into two parts, which will be deployed on the ground and which will be staying on the lander. So the point of this is that the part that will stay on the lander include electronics and source of laser, which needs to be kept warm. So they stay on the lander, which is much more easier to keep warm. And this part, which is a sensor head, which include this mirror and laser splitter, will be on the ground. But this sensor head itself have very robust temperature range from minus 80 to 60 degrees. So this don't need a so severe thermal control. So the idea is that we place it on the ground, which is pretty robust in terms of thermal, and we just keep on the lander, which needs much more thermal controlling. And this will also, we also have this tether, which is basically a optical fibers that we connect the two sensors. So we are now developing this. So this is the schematic diagram of the sensor head, and we also have this mechanical part. We also have this prism part. So this is now under development in IPGP with collaboration with commercial company EXBlue. So this is kind of like to give you some timeline of the observation. So this, we are now here, and we are trying to make a demonstrator of this optical BBB, and that will give us TRL6, which is good enough to propose to NASA missions or whatsoever by 25. In other words, every mission opportunity that will require delivery before 2025 will be something carbon copy of InSight seismometer, which is a mechanical seismometer. But if we can propose something, or we can deliver after 25, 7, 8, we would like to have this new generation seismometer, which is optical. So this is kind of our strategy. So here I put the figure of Altimus, but for Altimus, maybe we can go to optical seismometer. Finally, I would like to discuss a little bit on mission opportunities. So what are the opportunities that we can launch these kind of seismometers? So first of all, we have FirstSight Seismic Suite. This will be launched on 2025. This is simply a carbon copy of InSight seismometer. We just took the InSight seismometer sensor head and we just tilt it so that it can adapt to lunar gravity, which is not the same as Martian one. This is we already delivered the instrument to JPL, and we are just waiting on the shelf to be launched. And we also want to approach to opportunity of Altimus 3, which is the first crewed mission that will land on the moon. And finally, payload AO just came out on Monday. So we are now trying to propose our second, what we call FSS2, to this opportunity to have another seismometer on the moon. And what is exciting is that at least they say that this will be launched in December 25, which means that we might have a small network of 2 seismometers with FSS. So maybe we might have in the upcoming 5 years, we might have a small network of FSS and FSS2. And of course, we would like to have more approach to other CLIPS opportunities if there's any. And I would like to also mention some ESA. So there was an Argonaut or a former EL3 opportunity. We did respond to this RFI saying that we have a seismometer to place and we can make a geophysical station. So, but this is likely to 2030s. In other words, if this is really going to launch in 2030s, we would like to propose the optical seismometer instead of mechanical seismometer that we have for InSight. Finally, there is also a mission from JAXA. So JAXA is trying to make a seismic network on the moon. Actually, JAXA assigned the 3 scientific subjects that is a priority for them. And one of them is to build a seismic network on the moon. And this lead is kind of like a precursor mission that we'll do. And we are now trying to put optical seismometer developed by IPGP to this lead mission. And if this is successful, we will be targeting much more complicated, more network, wider network of mid-class standard which will be in 2030s. This is just a short figure to show you what kind of sensitivity we are aiming with optical BBB and FSS. So this line is FSS, but if it's going to be optical, we will go down much lower in noise level. So with that said, I will conclude. So first of all, I would like to say that the moon is exceptionally quiet place to do seismic observation. And there's many points that we gain by not having atmospheric activity nor ocean. And we are also making some efforts to take advantage of this condition and make some observation. And that is why we want to have this new generation seismometer, which can be proposed as a possible payload in 5 years. With that said, I would like to thank you and I will take any questions if you want. Thank you very much.